But let's finish up the problem we were doing before. So the problem we were doing before was H2SO4 versus H2SO3. So which one is the stronger acid? So is this a resonance form here if I move the hydrogen? No, it's not.
Right? Is that what?
Yeah, atoms don't move in resonance. So what should we do? Should we go ahead and just double bond it, or should we keep the octet and have formal charges?
Keep the octet.
Well, you know, different things you do, but you know, if you're ever in a situation where, you know, you're uncertain, what would the best answer be? The best answer would be show all of them. And so you could show this one, you know, and the other extreme. Like this. So here are the two versions of this, expanded versus not expanded. And then we had one more, right? That was in between the two, where we just had one double bond.
Do we draw all structure possible? All possible structure?
Yeah.
That's the answer.
That would be the best. You draw all the possible structures and then say it's some hybrid of it. But you could have arguments which one you would think would be the strongest. You could do that. In the past, you know, I've actually given this on the test. And in the past, you know, people have drawn all the structures. It turned out to be quite a long problem. But I did it for a different molecule. Now this versus H2SO3. When we look at H2SO3, that's a bit easier. This one would be the one with the expanded octet and zero formal charge. This one would be the one with the octet and maintaining the formal charge. So what to do? What to do? Now, when we're trying to analyze which is a stronger acid, you know, how do we analyze this? There are different ways we can analyze it. One way we can analyze these two acids is by looking. We want to make a fair comparison. And so the situation here is if we're going to keep an octet, then we should compare the two octet structures. And so we would compare this structure with this structure. If we're going to expand the octet, then we should compare the expanded one here with the expanded one. Which one? The one on the right here. And so we compare these two, or we compare these two. If we compare these two with the charge, then we just look at the formal charge. You know, the formal charge here is plus, formal charge here is 2 plus. And so which one has greater positive charge density? SO4, and therefore this one's going to have a greater, what do we call it? Inductive effect. And that's going to make this hydrogen more polar. Does that make sense? But you know, it's easier to compare these because when we compare these, we could just look at the oxidation state. And so what's the oxidation state on sulfur here? Plus 6. What's the oxidation state on sulfur here? Plus 4. And so again, here you can see +6 means in sulfate there's a greater inductive effect, which means it should be a stronger acid. And so in both comparisons, we see that sulfuric acid is a stronger acid than sulfurous acid.
Because of the charge, because of the positive, right?
Yeah, it's because of the
It
positive
makes
charge.
the inductive
Yeah, greater inductive effect, which means a greater
attraction.
positive charge on the hydrogen, which means more acidic. You know, the more H plus like the hydrogen is, the more acidic it is. Now let's compare the conjugate bases.
The better acid.
I'm going to compare the conjugate bases. The one with the expanded octet, like this, you know, even though we know maybe this isn't the most accurate because of having two, you know, PD pi bonds. But, am I recording this? Yeah, this is recording. How many resonance forms can I draw for this?
2.
So here, leave this one here. I could draw it down here. 2, 3. 3 resonance forms for this. You see that?
Yes.
So we're just looking at this. Versus, actually this isn't the conjugate, but we're just looking at bases right now. Versus sulfite. So sulfate versus sulfite. Which is a stronger base? Both of these have a -2 charge. A -2 charge is on the oxygen. And so which one is a better base? Sulfate or sulfite, and why? Yeah, this is the stronger base.
What is it?
What makes the stronger base?
Negative charge.
Negative charge.
Oh, because that one is more spread out, and then that one is more concentrated. Is that what? Because the negative charge on that one is like spread out throughout the molecule.
Yeah,
Is that why?
that's why. That's one of the reasons why. How many resonance forms do we have for this?
2.
Yeah, 2 more. And so when we think about this, okay, the negative charge is being spread out over how many oxygens over here?
4 oxygen.
4 oxygens, so that means each one of these is actually negative
-1.
2/4 or negative 1/2. And so each in the hybrid. Over here, we have a negative charge being spread out over 3 oxygens, so in the hybrid it would be negative 2/3.
So it has a higher.
It has a higher negative charge on each oxygen.
Therefore, it's stronger.
Yeah. Now, the other thing is this. The sulfur is what oxidation state?
Sulfur, 1 oxidation state.
This doesn't change in the hybrid either. It's +6.
+6.
And so having a +6 charge is going to pull in the negative charge density
From the oxygen.
from the oxygen. Over here, the sulfur is +4, which means it doesn't pull as much of the negative charge. And so this is going to be a better base because there's more negative charge on it, both from the resonance and from the inductive, right, point of view.
The resonance.
Yeah, that's how we analyze these. All right, the other way we could have analyzed this is we could have analyzed the other structures. Let's take a look at the other structures and see how we would have compared that. If we just kept the octet.
Professor?
Mm-hmm.
So when we say, like, when we want to decide whether it's a strong acid, which one is a strong acid, do we do the 3 methods? Or, like, if one satisfies, then we include that in it?
No, we look at it.
We look at all the 3 methods, right?
Yeah. All right, so here we have negative, 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 negative. And so what do you expect the real charge to be on the oxygens here? -1 or -1/2 or somewhere between?
Somewhere in between.
Probably somewhere between. -2/3 or -1? Probably somewhere in between. All right, now looking at this, can you see which one's a better base?
Better base?
Why is this one a better base?
Because yeah, it's because when you do wouldn't that one be more spread out, the negative charge?
Also, the negative charge, each oxygen is -1. This has only 3 oxygens and -1. This has 4 oxygens and -1. Shouldn't 4 oxygens and -1 be a better base? Yeah?
That's true.
Yeah. But we know also that this sulfur is +6. This sulfur is +4. And so there's going to be some inductive effect there. And so on the one hand, this seems like a better base because it has more oxygens with a -1 charge, but the inductive effect is going to pull it. On the other hand, this is going to have a weaker inductive effect, so maybe this is the better base. So how do you weigh this? Do you see these structures here are more complicated to analyze? This is why when I said
I'm going down.
when you analyze these, go ahead and expand the octet because it's easier just looking at the oxidation state, right? Rather than these with the formal charge. Otherwise, you're going to get totally mixed up. Does that make sense? And so even though it's somewhere in between as far as analysis goes, we'll go ahead and compare these because these are a heck of a lot easier to compare. You know, expand, minimize the formal charge, utilize d orbitals. Now, can we expand everything? No, we can't. No. Second period, we can't expand. No. Third period and beyond. Second period's the exception. Everything we can expand except for second period. All right. All right, I'm going to stop here. Now, how do we know? Well, we could test this. And how do we test acid strength? We test acid strength by using a pH meter. What we do is we mix up the concentrations roughly about the same and then see how strong the acid is. Stronger acids are going to yield more H+ in solution. So if I take a strong acid like H2SO4, H2SO4 is going to easily lose a proton to form some hydronium and, in this case, bisulfate ion. That would be the conjugate base here. Whereas something like acetic acid isn't as strong, so that hydrogen is held on there more tightly. In other words, water is going to have a hard time plucking that off. In fact, water can only pluck off about 0.1% of the acetic acid molecules to yield a very small amount of hydronium and acetate. And so here we should have a much higher concentration
pH.
of hydronium. Here we're going to have a much lower concentration of hydronium. When we have a high concentration, we call that low pH. And when we have a low concentration, we call it a high pH. And so they're inverted, they're flipped. And so acids have low pHs. You know, acids have pHs less than 7. And the lower, the more acidic. Bases have pH greater than 7. And neutral solutions have a pH of 7.
Probably water.
Like water. Water should have a pH of 7. And so today we're just going to do some simple pH measurements. You should see the stronger acids. You should be able to recognize the stronger acids because the stronger acids, low pH. The weaker acids are going to have a little higher, but still below 7. And then you can see the bases in comparison there. All right. And so I'm going to stop here, and then we're going to set up our experiment and collect some data for pH. pH readings just take a minute once you have everything set up.
Do we do it in the lab?